everyone, and welcome to today's Australian Airports Association webinar. Today's topic is runway friction and skid resistance for regional airports. We're pleased to welcome our presenter for today, Greg White. If you experience audio difficulty during the webinar, please dial the 1-800 support number listed at the bottom of the platform. I'll now hand over to Greg to begin.
Morning all. Hope you're all well. I see a fair old list of people joining us today to talk about texture, friction and skid resistance for airports, so that's always an encouraging start. Just a little bit of introductory. As you know, these sessions are facilitated by the AAA, but from my perspective, supported by what we do here at the University of the Sunshine Coast. This is a fourth, not a third. That's terrible. A fourth in the series. Been a bit of a break since the last one, almost a full year. One to go in the original series that we planned on pavement maintenance, which from memory is tentatively scheduled for sometime in September. All of these webinars have been loosely based on Airport Pavement Essentials, APN 12, and the intention's always been to focus as much of the content as possible on the regional, rural and remote airports. Although certainly in this case, most of the principles apply to the bigger regionals and even some of the capital city airports as well. Today we'll have a few definitions because I think, well, my experience is that sometimes a lot gets confused in terms of terminology, and making sure that we define friction, texture and skid resistance consistently is quite important. A bit of science, I promise, hopefully not too much science, but a little bit, just to try and understand some of the complexities that we're talking about and why some of these things are so difficult to write rules around. Some of the regulatory stuff, and in particular the MOS 139 changes, which by and large are positive and I think beneficial, but perhaps not perfect in all cases. And then some of the practical things. What does it mean for a small airport in terms of managing friction and skid resistance? Questions at the end, as always, but of course, if you've got a question on the way through that relates specifically to whatever we're talking about, then we'll take that as we go if we can. Otherwise, we'll try and make sure that we knock off any of those other questions before we get to the end. And of course, this is what we're all talking about, QF 747 in Bangkok in 1999, and like many aircraft skidding incidences, some combination of wet weather, questionable friction on that particular runway surface, and an aeroplane either landing long or going faster than it should have been at the time that it attempted to land. So in terms of a few definitions, skid resistance, and I always think about skid resistance as being the holistic thing. So it's really the ability for the runway to provide resistive forces to aeroplane tyres to allow the plane to decelerate. Usually on landing, to a certain extent, could also be an aborted takeoff. And my meagre understanding of airport planning is that the aborted takeoff distance is usually the critical distance in terms of runway length. But most of the time, planes are landing, not aborting takeoffs. What I'll talk about today really only applies to runways where speeds are high and braking forces are great compared to taxiways, aprons and other areas of the airport. And it really only applies to wet weather conditions because pretty much any surface that we could imagine has a pretty adequate level of friction when it's dry. In terms of surface texture, another important definition, texture is really the physical roughness or the unevenness of the surface. And in the friction and surface texture world, defined from a pavement perspective as either micro, macro or mega texture. And I highlight micro and macro in green because they're the things that really affect aircraft skid resistance. Mega texture, not so much. And it's certainly macro texture, which is probably the one that we talk about most often, is not intended to include grooves. So even though sometimes we think of grooves as being artificial macro texture, the FAA and NASA, who developed all the rules around grooving and friction and everything else, pretty much to do with airport pavements, it was always their intention that we shouldn't include grooves, and there are some very good reasons, probably beyond the scope of today's discussion, for excluding those. Bit of a picture, it's got a bike instead of an aeroplane, but the principles are the same. At the biggest wavelengths, you've got roughness, which is really, am I going uphill, downhill, or am I feeling a bump? And then down from there, you've got mega texture, and that's really about, does the surface feel uneven or corrugated? Can I feel the vehicle or the plane vibrating as I'm trundling down this piece of pavement? That's the mega texture, not really what we're interested in today. Then we've got the macro texture, which is really the spacing in and around the particles. And then the micro texture, which is actually a characteristic of each individual particle itself. So moving from surface texture, which is a very physical thing, you can see it and it's a bit easier to measure, to friction. And friction is the force that resists the movement between two bodies that are in physical contact. It comprises static friction, which is essentially if something was sitting still when you tried to push it, there'd be some static friction. Once you get it moving, there would also be some kinetic friction or dynamic friction, if you like. And this is one really important thing to get your head around, is that friction doesn't change because there's moisture present. The actual friction that is inherently in that surface is still 100% there. It's just that it's being blocked or hidden by the presence of the moisture. So when we actually talk about a friction test on a runway, we're not actually measuring true friction. We're actually measuring the effective friction, taking into account the 1 millimetre film of water that we're putting on the surface immediately prior to it. So it really is a friction minus the effect of moisture, as opposed to true friction, which would need to be tested in a completely dry situation. And as I said, we're really talking only about runways, and we're really not talking about dry conditions. We're talking about wet conditions when we talk about friction and skid resistance on airports. So a bit of science, and for those who don't like this stuff, sorry, I'll try and make it, I've got lots of pictures, so hopefully that'll help. Some micro texture, the very small texture, actually provided by the interaction of the asperities. And the asperities are just is a technical term for it affect the very small microscopic unevenness or protrusions between the two surfaces. And every surface has them. It's just a matter of how far they stick out and how frequently they occur, that you effectively make something rough or smooth to touch. And that really comes from the aggregate particle surfaces, so the individual particles. Macro texture also contributes to friction by hysteresis, which is essentially how the tyre bends around the unevenness or the macro texture in the surface. And it's provided by the space between the particles, as we've already talked about. We know that pavement moisture hinders friction, and we also know that effectively the macro texture allows that moisture to escape. So think of macro texture as being the inverse of the tyre tread on any tyre, which is allowing that water to escape from between the tyre and the pavement surface. Typical aeroplane tyres, you can see there that the tyre tread, unlike our car and even my motorbike tyres, is circumferential, so it runs around the tyre rather than transversely across the tyre. a couple of images on the right-hand side that show this idea of adhesion being effectively the force resisting the movement of the tyre and the pavement surface or the particle, and then the hysteresis being how the tyre bends around that little particle or that little lump in the surface. And a bit of credit to my friend Jamo for producing this image as part of his master's thesis, which was on ungrooved runways using stone mastic asphalt, which he'll present at the AAA Pavement Mining Forum in May. So a little plug for Jamo's good work there. But really what we're talking about is how much water or how much moisture we've got between the tyre and the pavement surface, and how much that effectively hides the friction that is available. How do we test these things? We're reasonably rudimentary, but we do our best. The sand patch test in terms of macro texture, so it only measures macro texture. It doesn't measure friction. We end up with this sand circle, and the bigger it's a controlled amount of sand, the bigger the circle, the less texture there is. In terms of friction, we can use this device called a British pendulum. It effectively does a spot test. We do pre-wet the surface, but it's extremely difficult to control. It's a dynamic friction test, which is relatable to micro texture, and to a small extent, if we do it wet, to macro texture, because that'll give us an idea of how quickly the moisture moved away from the surface. And you'd like to think that the pendulum plus the sand patch test result would give you a pretty good feel for what friction levels or skid resistance levels you've actually got on your runway. I'm not quite convinced that is necessarily the case. And then grooves are the other thing. Most of us would be familiar with grooves. It's artificial or synthetic texture. It also provides a path for the water to escape between the tyre and the pavement. It's not really for general pavement drainage, so just because you can't see the water doesn't mean that your grooves are or are not being effective. As we know, they've traditionally been 6 mils by 6 mils at about 38 millimetre spacing. Interestingly, the UK has smaller grooves at tighter spacing. In the USA in the last few years, trapezoidal grooves have become more and more popular. They have larger volumes of grooves at a greater volume or greater spacing to effectively provide the same amount of volume. People quite often ask why they sawn transversely across the runway, and it's really because that's the shortest escape path for the water. So here's a real runway surface, or a photo of a real runway surface, I should say, and imagine that's the tyre contact, and you can see the tread patterns on the tyre consistent with how we saw them on that actual aircraft tyre running along or parallel to the runway centre line. So the shortest path for the water to escape is transversely across the tyre, which is why the grooves are sawn in that direction. So in terms of skid resistance, what we're really interested in is the effective runway friction, because that's the skid resistance that our surface is going to provide to the aircraft. And I always think of that as being equal to the actual friction, which is the friction available in the complete dry, minus whatever reduction the moisture is causing. And we know that our friction test is a wet or an effective friction test. These are our continuous friction surveys now we're talking about. The degree of wetness is very specific. Effectively a 1 millimetre water film placed on the surface just in front of the tyre, the test tyre. And it's at very specific vehicle speeds, 65 k's an hour and 95 k's an hour, noting that aeroplanes typically land at about 180 k's an hour. So we're still quite a way from the actual speed that the aeroplanes typically land at. And if you think about it as the effective friction being a function of the micro texture and the macro texture. As I said before, you might like to think that one day we could relate a British pendulum and a sand patch test, which would be a lot easier and quicker to perform than a full-length friction survey. We might be able to combine those two results to calculate the effective friction, but we're certainly not there yet, and I'm not sure that we will be anytime soon. The reason why we test at two different speeds is that the speed is important. The speed is important to the results of the test. The quicker you go, the more the water will hinder the friction that is available or impede it, and the lower the results will be. So at low speeds, the water has got plenty of time to escape, and you can achieve almost your full friction if you go slow enough. But at high speeds, the water doesn't have time to escape, so the amount of reduction from the true friction to the measured friction is more significant. The more macro texture you have, the quicker the water, or the more efficiently the water can escape, and that amount of reduction will be less and less. And that's why it's critically important for runways that we test our friction wet and fast, which is why you've got the 95 km/h test with the 1 millimetre water film just in front of the tyre. So a typical friction survey, for those who haven't had one done at their airport or haven't stayed up until 3 o'clock in the morning to actually see one being done at their airport, typically at 65 and 95 km/h, 3 metres and 6 metres each side of the centre line in both runway directions, so north and south if you're a north-south alignment, which gives you full 8 runs, full-length runs of your runway, plus a couple of calibrations. There are currently, I understand, 9 different machines that are approved or endorsed by AAA for performing those tests. There are 2 or 3 different machines in Australia. Most of the test results I've seen have been done using a grip tester, but there certainly are others around, and they have some pros and cons, but we won't delve into that today. Typically, you'll get your report. It'll give you an average for every 100-metre length of your runway. So if you've got a 3-kilometre-long runway, you'll get 30 100-metre results. If you've got a 1,500-metre runway, you'll get 1,500-metre length results. Quite commonly, you also split the runway into thirds, which is effectively touchdown zone, central portion, touchdown zone, and that really reflects the significant impact, particularly at the busier airports, of tyre or rubber contamination and build-up over time with repeated landings in the touchdown zones. It's important to understand and to recognise that test temperature has a significant effect on the results. So you'll get swings from nighttime to daytime tests. You'll also get swings from summer tests to winter tests of the same surface, even in the same condition, because of the different temperatures, which primarily affects the hardness of the tyre that's doing the test. The tyre condition can affect things as well. A worn-out tyre versus a new tyre can have a significant impact on the results. And of course, your surface will change over its lifetime, hopefully 12 or so years, maybe 10 out of a runway surface, and in that time, the friction that it provides or possesses, certainly the wet friction or the effective friction, will change as well. Specifically, if you treat by removing rubber, then you get more contamination. You might do a preservation or rejuvenation treatment. And even if you had no traffic, you would still change over time just because of the oxidation and ageing of the surface. The FAA and ICAO tell us we should ignore the last 150 metres of the test because you could imagine getting up to 95 kilometres an hour from a standing start at the end of a runway takes a bit of time. So that last 150 metres is generally omitted. And of course, the 150 metres at the other end, the vehicle slowing down before it runs over the end of the runway, which quite often has got lights if you're at a regional airport, elevated lights. So you've got to take those last 150 metre segments with a grain of salt. There's always a question about what do I do if I get one bad result? What if I get 100 metre length with an average bad result? Do I shut the runway? Do I put out a NOTAM? What do I do? So they're all the challenges and the practicalities, because there's no clear, hard rules around what you do in those circumstances. For those that haven't seen one, that's the unit. So you've got basically a big yellow bladder full of water in the back of a ute. You've then got this little trailer with a semi-fixed wheel and a few smart sensors. It's all hooked up to a laptop computer. The water gets put on the surface just before the wheel that's under the little yellow trailer at the back, and then the computers do the rest, essentially, and that's probably all you and I need to know about the system. Here's some typical results. They happen to be from Brisbane Airport. You can see the 3 lines, red for minimum, yellow for better start thinking about intervention, blue is all good, and then the very orange line right at the top is effectively what you might expect from a brand new surface. You can see there some dips in the touchdown zones, and that kind of data is what prompts rubber removal on a periodic basis at some of the larger airports, and indicates good friction and general compliance through the majority of the length. Some other things that I personally think we should be taking into account when we're making decisions about friction and surface texture and skid resistance is the length of the runway versus the aircraft. I quite often say if you're landing Saab 340s on a 4 kilometre long runway, you're not going to have to worry too much about skid resistance, because that plane is very unlikely to ever have to hit the brakes hard. Similarly, if you live in a place where it rains a lot and it rains heavy, then you're going to have a thick water film on your runway quite often, compared to if you live, let's say, in the centre of the country where it doesn't rain very often, and so your risk profile would be significantly different. You could also wonder about runway crossfalls, and if you're in a runway intersection or the intersection between 2 runways where your crossfalls are always going to be quite low and effectively a flat spot, then that presents a different level of risk, again, because the water won't drain as quickly, which means you'll end up with a thicker water film than you might otherwise end up. You might end up with if you've got a very high crossfall, 1.5 or 2%, which you might typically have on the rest of your runway. I think it's fair to say, and I've researched this in great detail, so I'm just borrowing some stuff I found when I just Googled runway skidding incidents, is that most of these incidents have a combination of poor weather, some kind of long landing, pilot indecision, usually in terms of land, no take off and go around, no land, and some questionable level of runway surface condition, usually from either not being grooved or having been preserved or rejuvenated in some way. Most of the incidents have those 4 things in common, according to Google. I just like that picture as I found it, so I thought I'd try and find somewhere in it somewhere to plot it in. I think that was actually a test track where they were measuring skid resistance or experimenting with skid resistance in very highly contaminated runway surfaces. I understand that there wasn't actually a pilot driving that aircraft, it was on remote control, which I thought was quite interesting in itself. So we're regulations. What are the rules around all this? And I think it's fair to say, and I think there are a couple of CASA people on the webinar, and I don't think they would argue, because we've had this discussion numerous times, is that the current MOS isn't as clear as it could be in relation to some of these issues. My simple interpretation is you've got to have a millimetre of surface texture, which you'll get from a spray seal, you won't get from ungrooved asphalt. Or you've got to groove it. So effectively, if you've got a grooved runway, an asphalt runway, you're probably going to need to groove it because you won't have the 1 millimetre surface texture. Or you need to demonstrate and maintain your wet friction level above the ICAO minimum values, which are published in the MOS. if you're an international airport, then the friction testing becomes basically mandatory. But the obligation to either have grooves or a 1 millimetre surface texture is the normal or most common demonstration of compliance for most airports. It's worth mentioning at this point that more and more airports are asking me or telling me that their CASA inspector is asking for evidence to support one of those methods of compliance, which probably hadn't occurred as often in the past. So I think that just demonstrates how important skid resistance is, and that from a regulatory perspective, it's certainly on the inspector's radar. In terms of the new MOS, it's made a good attempt to try and address some of the ambiguities. I would say that it's gone a long way to resolving some of these things. There is probably some frustration because of the way lawyers want things worded and the perception of risk, and in a lot of ways unknown risk, because to be frank, we don't really know the risk of not complying. So if you don't comply and the risk is very difficult to calculate, then it makes it hard to objectively change the rules, because you're changing the level of risk without knowing the current level of risk, if that makes sense. But there are a number of significant improvements in the new MOS. It does a much better job of recognising those three means of compliance: surface texture, grooving, or friction testing. So that's a great thing, in that that's now quite clear, or much clearer than it was. Based on some FAA guidelines around what a minimum surface texture should be as opposed to a new surface texture, the 1 millimetre has been reduced to 0.625 millimetres, which I was a little surprised by, but this probably recognises that we'll hit 1 millimetre when we're new, but things will change over time, so that's probably a good thing. There's some more or clearer methods and protocols around testing friction, specifically in terms of band patches and how many and where they should be and how often you should do them. So that's a good thing, particularly for regional airports with spray-sealed surfaces. And there's also a recognition that line marking reduces friction, but line marking is very small in terms of the square metres out of an entire runway. So there's some exclusion around line marking, or recognition that line marking changes the playing field, and you can't have line marking with the same level of friction as the unmarked surface. It's just not practical. It's probably important that I note that that's all still draft, so that's based on the current draft, but that's not necessarily what will be issued, so you just got to take that in that context as well. There are still a few challenges in terms of the regulatory stuff. There is recognition that the last 100 metres can't be tested, so there's a waiver, but to be honest, in my view, the waiver's meaningless because it says that you can ignore the results in the last 100 metres, but you've still got to either have a millimetre surface texture or groove it, which defeats the whole purpose of complying with the wet friction test option anyway. And it was always my suggestion that it should just be the last 100 metres of runway, that's the run-up speed for the friction test. All bets are off, don't worry about it, because if you're relying on that last 100 metres, you're probably in strife anyway. But that's not how the current words read. There's still no guidance on how to react. So as I said before, if you get one bad result, what do? Do you shut your runway? Do you issue a NOTAM? Do you immediately do something? So there's no guidance on that. So what's probably good for big airports that have very sophisticated management systems to have loose guidance around that so that they can make informed decisions. It might be useful for the smaller airports to have a very firm, in this event do this, in that event do that. That's currently not in there. And the guidance on testing frequency there's some there, but particularly for the friction survey testing. It's still not very specific. So Ian's just made a comment, thank you Ian, that if you're below minimum levels, then you should raise an OTAM and do something without delay. I don't think anybody disagrees with that. I think everybody absolutely agrees with that. The question is, what if if I've got a 3 kilometre long runway and I've got an average of 100 metre results, then if one of those is marginally below and the other 29 results are perfectly good, do I react in a different way? And I think the answer would be yes. Then if, say, 50% of my 100 metre average results were questionable or below the minimums, I think that's where the lack of clarity perhaps sits. But that's okay. In terms of some of the practicalities, well, we've got a couple more questions, so we might try and do those before we go on to some of these practicalities. Would you agree that the new MOS would better support a dense graded runway not being grooved, assuming that it meets the current levels? And would I have any concerns about grooving a 3-year-old surface? So the second question first, I think in the long term, I'd be very concerned about trying to groove an 8 or a 9-year-old surface. 3 years, perhaps certainly less concerning from particularly a ravelling and surface tightness perspective. 3 years, probably okay. 8 years, probably not okay. What's the transition from one to the other? Don't really know, but your gut feeling says you'd have to look at this particular surface to make a call on how eroded it was. In terms of the new MOS, if you accept my interpretation of the current MOS, I don't think it really changes significantly whether or not a dense graded runway should be grooved, because my interpretation of the current MOS is if you're willing to get a friction test every 12 months or every couple of years, depending on what you think is the appropriate frequency, then I don't read the current MOS as requiring you to groove as it currently stands, unless there might be some caveat on that around being an international airport. So no, I don't think it makes much difference. I think where it will make a significant difference in terms of what a particular airport has to do is an airport with a new surface that's got a surface texture level in the 0.8, 0.9, 1 millimetre. All of a sudden, that is now acceptable, whereas before you would have been chasing that 1 millimetre all the time. Now, my experience is dense graded asphalt without grooves will give you a surface texture of 0.4 to 0.6. So you're probably still below the 0.625. But really, the new MOS hasn't intended, apart from that change in the minimum texture, surface texture, hasn't really intended to change the requirements for skid resistance and friction. It's really just tried to clarify them, and in particular the testing and the frequency of testing, more so than change the actual intent or the requirement that you're chasing. So back to some practicalities. If you've got a sprayed sealed runway, if you've sprayed sealed the runway well and it's to what I call a typical airport design, you'll have more than a millimetre of surface texture and you'll be all good. But there's a good chance in the future somebody's going to ask you to demonstrate that, not just rely on the fact that you've got 1 millimetre or you've got a spray seal. Yep, where's your data that backs it up? So that'll be the question that you have to be able to answer. If you've got an ungrooved runway surface, as I said, you'll have probably between 0.4 and 0.6 millimetres of surface texture. That will increase over time, but it will take a long time to get anywhere near the 1 millimetre. You might be lucky and get to the 0.625 on day one. You might not, probably not. If you friction test it, it might be okay, but it might not, because then you're relying on a whole bunch of different things to just get you over the line in the short term. So in practice, you're probably still going to have to groove. Now, I mentioned at the start, Jamo, master's student who was here last year on secondment from Defence, his project was about stone mastic asphalt as an ungrooved runway surface. Stone mastic asphalt has between 1.1 and 1.3 millimetres of surface texture and therefore meets the 1 millimetre requirement. Certainly will meet the 0.625 millimetre requirement of a new asphalt surface on a runway. So that gives a lot of small airports who would have resurfaced with dense graded and grooved an alternate to avoid grooving, therefore avoid groove closure risk, and you not have to pay somebody to groove their runway. He'll go into that in great detail at the Pavement Mining Forum. And then, of course, you've got to groove your runway. That's potentially that's really bad. I think my computer's just turned itself to sleep because I hadn't pressed the button for too long. So just bear with me whilst I try and get myself back. There I am. That's a bit odd. So if you've got a groove runway, you're effectively compliant because you've got grooves, but you do need to monitor them for rubber contamination and for erosion. A question from Canberra Airport: will the new MOS allow for trapezoidal grooving? It's one of those really strange things that even though the MOS says that grooving is, current MOS says that grooving is one of the ways you can comply from a skid-resistant surface texture perspective, I don't believe that the MOS has ever dictated what a groove looks like. I can't recall ever seeing anywhere in the MOS that it says a groove must be 6 millimetres by 6 millimetres and 38 millimetres spaced apart. Which I find quite interesting. And if I'm correct, and I think I am, if that's correct, then the current MOS doesn't really prevent you from using trapezoidal grooves in any way, shape or form. It'll cost you a bit more, so it'll probably be an airport-specific decision. Question from Brenton is about the aggregate size. So that's to get the 1.1 to 1.3 millimetre surface texture depth. So the trials that we've done to date are on a 14 millimetre mix. So it's a 14 millimetre mix. It's actually very, very similar to the stone mastic asphalt that Queensland Main Roads uses on a lot of its highways around southeast Queensland. It's actually been modelled off of the Chinese specification. China's got like 40 ungrooved runways, and they're all the big ones: Shanghai, Beijing, all those big airports in China. A significant portion of them are grooved. Stone mastic asphalt, and I think they use a 13 millimetre mix, but that's just because their seed sizes are a bit different. It's basically all the same 14 millimetre mix, which is comparable to our current dense graded mix designs. There's a question from Jared about the new MOS, and it refers to having a minimum design objective in terms of the friction levels. Yes, that's the intention of the new MOS was that it would only have the minimum that you needed to achieve. It wouldn't tell you because what I've never understood, if the minimum is of 6 is acceptable, why would the regulation say, but I need to achieve 10 on day one if 6 is the minimum? Surely all I need to do is achieve 6 on day 1, day 2, day 3, and every day thereafter, not achieve 10 on day 1, and then for the rest of the surface of life achieve 6. So I think that's been clarified well in the new MOS. So back to some of this practical stuff. I think what not to do is just as important as what I think you should do. But my suggestions are: don't resurface your runway with asphalt without thinking about surface texture or friction and how you're going to comply. Because, as I said, CASA inspectors are asking more often about where's the evidence of compliance, which is a fair thing to ask, and so you're going to have something in place to be able to answer that, and it'll have to be evidence-based. And I think the new MOS clears that up quite a bit about what that evidence can be. Don't average the texture you measure in your flushed wheel paths with the texture you measured on the edge of the runway and say, well, on average, if I take those bits and add them together, I'm okay. Because really, the aeroplanes need the bit in the wheel paths. But they don't rely as much on the bit on the outside of the runway. And yeah, I've actually seen reports where that's been done, and it made me shake, to be honest. Don't contemplate a rejuvenation or some other treatment of your surface without thinking about how you're going to control and manage and verify your friction as a part of that process. But I also don't think you should overreact to one low result. Remember, a friction test result can be affected by the temperature, the time of the year, how well how worn the tyre on the machine was, how fast the guy or the person who was supposed to be driving at 95 kilometres an hour actually drove. So there are a range of things to think about before overreacting. I've seen this a few times as well, which is a small patch in a runway, and then people want to immediately groove it because if 1 square metre is not grooved, they consider their whole runway ungrooved. And the FAA provides quite detailed guidance on small areas of non-compliance, and it's got to be a very large patch before you should rush out and actually groove a patch. But most importantly, don't not have a skid resistance plan of some description. It only has to be a couple of pages, details how you comply and what your current results are and what your next step should be. I've seen a few airports put that little plan, which is pretty simple, into their airport manual, and then they're happy, and when their CASA inspector or their AGI inspector comes around to do their duties, that's sitting there with all the rest of the airport operating documentation and makes it clear how the airport's managing skid resistance, whether that be by friction, by grooves, by whatever the case may be. It's just a photo of, this actually came from that report I was saying about. They had 2 millimetres of surface texture plus on the edges and 0.5 in those 2 wheel paths, and that was somehow given a weighted average of 1.2 millimetres and given the green light, which I thought was highly inappropriate and not the intent of the current MOS or the new MOS, despite the fact that the wording in the current MOS around the term average surface texture probably isn't as clear as it could be, and certainly that's been cleared up a bit in the new MOS. Unanswered questions, I think there's a couple. When reviewing friction results on a grooved runway, should we take the zone average as an optimal number of where to remove rubber? Yeah, so I think the question is, do you necessarily remove rubber from a 100-metre section, and how many of those 100-metre sections should you remove it from? My view would be that you would where you start and stop your rubber removal would primarily be based on a visual inspection of where you've got rubber contamination. And given as much cost of rubber removal the cost of rubber removal is as much about getting the machines there as it is about doing the actual work. I think you would take a conservative view and do more, not less, because by the time you've got them there, it's probably not that expensive to do an extra small bit. Jess from Adelaide asks, how small is too small to groove an asphalt patch? Well, as I said, the FAA actually provides some guidance on that. I think their terminology is something like, from memory, if 500 feet, which is about 150 metres, of your runway has grooves that are less than 40% of the volume that they're supposed to be, which is what an asphalt patch would be, because there'd be no grooving volume, then you need to consider that as an issue. So the implication is if your patch is less than 150 metres long, which is a really, really big patch, then under that particular piece of guidance, it wouldn't need to be grooved. Now, I'm not sure that I would necessarily support that in a lot of cases, and again, it's written very loosely in that it doesn't really say how much runway would need to separate, grooved runway would need to separate that patch from the next patch. So I don't know that there's a specific answer, Jess, but I think it would just be fair to say that one small patch doesn't necessarily justify grooving the patch. 50 big patches probably would, and there will be a cut-off somewhere in there, and I can't say I know what the answer to that specific cut-off is, and it's probably a question for the individual airport based on all of the other things we've talked about: length, planes, international versus domestic operations, the friction levels otherwise, and the environment that airport is in terms of its climatic conditions. I don't know that you'll get a more specific answer than that, I'm afraid. Geraldton Airport asks the preferred method for rejuvenating a grooved asphalt runway. Carefully would be probably my only suggestion. Certainly, there have been a number of runways that have been rejuvenated or preserved with sand-filled products, non-sand-filled products, old cutback bitumen in the days when cutback bitumen sets were the normal preserving or rejuvenating treatments. Grooved and ungrooved, you've just got to be careful doing it. And the most important thing is you don't fill the grooves up with your product. And my experience is the best way to avoid filling the grooves up with your treatment product is multiple applications at a very low application rate, as opposed to one heavy application. And I always say it's a bit like painting your wall. If you grab a bunch of paint and splash it on the wall, you'll get dribbles and things will run. But if you put that same amount of paint on in multiple light coats and allow each coat to dry before you put the second coat on or the next coat on, then you'll avoid the ability for the material to run, and you'll therefore won't fill your grooves up usually. But most of those products are going down at very low application rates anyway. But be careful and do a trial and be sure and confident that about the effects of that treatment before you just go holus bolus and do the whole lot and then wonder what to do afterwards. I think that's where we're supposed to be up to. No, I don't think it is actually. I think that's where we're supposed to be up to. So really, just to summarise, and if a couple more questions come through, we'll get to them when they arrive. But clearly, skid resistance is a critical part of aircraft safety, which is why regulators and inspectors are probably more focused on it than they perhaps were in the past. It's an extremely complicated issue. It's an extremely complicated issue, and measuring it repeatedly and reliably is quite a challenge in itself. The MOS mandates what internationally is only guidance. So we've made some things compulsory in Australia that most of the rest of the world, or certainly ICAO, considered to be advice and guidance to be managed at the local level. And that generates a few challenges. The new MOS makes some significant improvements in those things, but there's still some challenges in terms of the new regulations. And there are lots of options. So an airport has a number of options in terms of how it meets its aircraft skid-resistant obligations. So consider those options and pick the one that best suits your particular airport. But don't just put your head in the sand, because one day your inspector or your ATI inspector or your CASA inspector is going to ask you for some proof or some evidence about how you're managing skid resistance. And I think the overwhelming intention is that you've got a reasonably sound answer and some evidence to back it up. And this is the point that I always say, that we should all just be thankful that it doesn't snow on our runways. Because whilst we've got to deal with water and friction and those kinds of things, we don't have to deal with contamination from snow, and that's got to make our lives a heck of a lot easier. That's pretty much the end of me. Hour's not far from being up anyway, so thanks. Feedback's always welcome. I think I mentioned the next one's in September, and it'll be on Pavement Maintenance, and they're my contact details. So if you've got any other questions or just want to have a chat, just feel free to get in touch at your convenience. Thank you.
Greg, thank you so much. For those of you who don't know me, my name is Samantha Layton. I am AAA Policy Manager. I'd just like to personally thank Greg for an informative presentation, and thank you all for participating. Greg is one of the many industry experts who will be presenting at the AAA Pavement and Lighting Forum in Melbourne this May. The forum is the only event of its nature held in the Asia-Pacific region, and delegates can hear about the latest technology and case studies whilst networking with industry stakeholders and peers. We ask that you now take a moment to complete a short webinar survey that you will see on the right-hand side of your screen. Please ensure you hit the orange submit button once you've completed all the questions. And for any further details of the next AAA webinar, you can contact us at airports.asn.au. We will also have a link to the register distributed by Redback shortly after. Have a wonderful afternoon, everyone, and thanks so much, Greg, again.